Okay, so again, thanks for the invitation. So today I want to talk about risk measures, and particularly robust risk measures with application in finance. And this work this presentation is based on a collection of work that I've done with a few collaborators. So I will first talk a little bit about what is kind of robust risk measures and why would we want to consider robust risk measures. And then I will look at two examples in portfolio optimization. So that will be based on the first two links there. And then I will kind of in the second part of the presentation look a bit about dynamic robust risk measures. So the work on the static case, kind of the first paper that's based on is together with Carol Bernard and Stephen Van Duffel, and then the application to portfolio optimization is with my colleague Sebastian Giamongo, and then the dynamic case is with two people from Concordia University, Marlon and Melina. So let me kind of go and talk a little bit about the motivation. Probably a lot of you already know why we should consider or robustify, but let me kind of put the setting. So we're interested in a risk measure. So my role is going to be the risk measure. It takes a random variable and gives a real number and quantifying the risk. So of interest is my rho of x, and typically what we want to do is we want to robustify this risk measure. And so how do we robustify, and what do we mean with this? So here in this talk, I typically talk about distributional uncertainty. So for example, you could think you have some data where you estimate your random variables. So for example, you want to have an estimator of your, let's say, value at risk measure. So you have an empirical distribution, for example, or you have a parametric distribution that you estimate. And of course, could be uncertainty in your data. That could be missing or incomplete data, or you could have a misspecification of your parametric assumption. So there's some uncertainty in your underlying distribution. You could also have model uncertainties, or if you think about excess, for example, an aggregation of different risk factors. So then you could have dependence uncertainties, or you wouldn't know the copula between your risk factors, or you could even have uncertainty in your aggregation function. And there's a huge literature on robust optimization, where you think that I want to find the best action in the worst case. So we will look at that in a portfolio optimization example, where you try to find a portfolio strategy that performs best in the worst case. So if your model is not a kind of specified. And there's as I said, multitude of application in robust decision making, portfolio management, hedging, and also partial identification in economics. So what is a worst case risk measure, or kind of how do we incorporate uncertainty? So typically what we do is we take a risk measure. So the risk measure is given that we're interested in. We have the random variable x, that is our risk. And then we look at the worst case value that risk measure can attain if my x is misspecified. And one way to put this mathematically is saying that x belongs to an uncertainty set, where u here is a set of alternative plausible random variables, or if rho is lower invariant, a set of distribution functions. So the question then comes as, how do we specify or characterize such an uncertainty set? And of course, there's a trade-off between the uncertainty set being too small or too large. Right? So if it's too small and just a singleton, then we don't robustify anything. We just calculate the risk of our random variable. If U contains too many distribution, then the supremum is just fairly large, or even plus infinity. So it's kind of an art of trying to find a good way of characterizing or quantifying such an uncertainty set. So I want to give an example of that. So this is an uncertainty set that's been considered in the literature kind of quite extensively. So here people assume that you know or have a good idea what your first two moments are. So you say you have your data, you can reliably estimate your mean and your variance. So let me consider all distributions that share the same first two moments. So that will be my uncertainty set. I look at all possible distribution that have the same first moments. So what you then can do is you can look at, okay, what is the worst case value at risk if I have a fixed mean and variance? And that's been considered in the literature. So here, these are typically called risk bounds. So here I have three risk measures. So the value at risk, which is the quantile at level alpha, then the range value at risk, which is the integral of the quantile from alpha level to a beta level, and then the expected shortfall, which is the expected value of the risk given that you're larger than the value at risk. And here in brackets on the left side is the best case, which would be the infimum over your uncertainty set, so the smallest value the risk measure could attain, and on the right side will be the largest value. So you could view this interval as an uncertainty kind of set, kind of uncertainty about possible values of your risk measure. What is nice about this is because you can actually calculate it analytically, there are mathematical nice formulas, but there's a couple of drawbacks to this. So let's look at a couple of examples of alpha that are typically used in risk management. So here I look at the right tail of the value at risk and expected shortfall. So if you choose alpha to be 0.9, this ratio of the square root of alpha divided by 1 minus alpha is equal to 3. So if you look at the expected shortfall, that basically means the range of the expected shortfall could be anywhere from its mean to the mean plus 3 times the standard deviation, which is fairly large. But if you take alpha to be, let's say, 0.99, which is typically required by regulation, then this root becomes basically a factor of 10. So it says that while your expected shortfall should be, or could be, the worst case it could take on will be the mean plus the 10 times the standard deviation. So this is fairly large, and in practice, at least, fairly not really useful, because this is a number that is so large that it won't really kind of happen in reality. Well, another drawback is that these worst case only depend on the mean and the standard deviation of your distribution, right? It doesn't have any other kind of information about your random variable x. So for example, if you look at the value at risk of a normal or a log normal or a Pareto distribution, or even a uniform distribution, if they share the same mean and standard deviation, well, then the worst case value at risk is always the same, right? Even though their value at risk will be very different. Moreover, if you look at the quanta function that attains these worst counts, these are 2-point distributions. So these are kind of a bit undesirable. So there's been quite a lot of work on how could we create or choose a better uncertainty set. And the idea there is mostly to incorporate more knowledge or more constraints on the uncertainty set, so making it smaller. So you could, for example, include higher moments constraints. So you say the third and fourth moment. You could have symmetry, so you only consider distribution that are symmetric or unimodal. But these lead to kind of only marginal improvements, and typically that the worst case distribution is discrete, right? So if we say your baseline model is a normal, then your worst case distribution is discrete, that might be not satisfying from a practical point of view. So one example that I wanted to share here was the work that I did with Carol and Stephen, where we looked at an uncertainty set created by the Wasserstein distance. So here it's a slightly different approach. We have a reference distribution, which could come from your data being estimated, the empirical distribution, for example. And then you look at all alternative distributions that are close to this reference distribution, and closeness here is characterized via the Wasserstein distance of order 2, which is given here in this formula. So there's a few formulas, but this formula that I wrote down here on the slide is kind of quite intuitive, because what you look at, you allow for all distributions that are close by. So the quanta function has to be close by in the L2 distance. And here the epsilon is basically your tolerance distance and how certain you are about your reference distribution. So if you do this, what we looked at in that paper was a specific class of distribution risk measures, which are distortion risk measure, specifically coherent distortion risk measure, which are given of this form. You integrate the quanta function, and then you multiply with what I call gamma, which is a density in 0, 1. And any density gamma gives rise to a distortion risk measure. And here what we require is that gamma is increasing, which then gives you a coherent risk measure. So again, what you can do here, you can look at the worst case. You take the supremum over alternative distribution function, where g's that lie within an epsilon kind of ball around the reference distribution, where the ball is characterized by the Wasserstein distance. So what you can do is you can fairly nicely calculate that. So the worst case is the risk measure of the reference distribution plus your epsilon, which is your tolerance distance, and then kind of a factor that depends on the choice of risk measure here. And you can also write down the worst case quanta function, which is also quite nice. So it's kind of a linear combination of your quanta function and the risk measure. So here, and since by assumption gamma is increasing, this defines a valid quanta function. So this is all nice, but again, there's a few caveats. And if you look at the form of the worst case risk measure, right? So what we have is the worst case risk measure is the risk measure plus a constant, right? And this constant does not depend on the reference distribution. It only depends on the choice of risk measure. So this might be not satisfying if you, for example, look at your F distribution is the kind of your portfolio wealth, and you want to optimize, you want to find the optimal kind of strategy that minimizes or kind of the worst case risk measure, because you will get the same optimum if you don't look at the worst case risk measure, because the worst case risk measure is just plus a constant, right? So to kind of make this constant, or the worst case not only depends on the risk of your reference distribution plus a constant, what you could do, or what we were thinking was, how about we kind of take the intersection of these two uncertainty set. So we were looking at the following uncertainty set. So we still have a reference distribution, but we assume we know the mean and the standard deviation of this reference distribution. So here denoted by mu and sigma. And then we define our uncertainty set as all distribution functions that share the same mean and standard deviation as the reference distribution, but also that lie within, an epsilon distance of the reference distribution, again specified with the Wasserstein distance of order 2. So this is kind of the combination of these two reference distributions, these uncertainty sets. And then you can look at the worst case distortion risk measure. And what is here is interesting, that you get two different cases. So you get the case where epsilon is small enough so that the Wasserstein distance actually matter. And then you get the case where epsilon is large enough and the Wasserstein distance is irrelevant, and you end up with a case where you only kind of have an uncertainty set that cares about the first two moments. So here I denoted that by the two cases. So if epsilon is smaller than this constant here, what we get is the following worst case quanta function. So what you see here, it's again a linear combination of your quanta function, your reference quanta function f, and the risk measure, which kind of distortion risk measure gamma. But you have a few parameters here. So the lambda a and beta b lambda, these are such that the quanta function has to write the same kind of mean and variance as the quantile, and then the lambda there is the solution such that the Wasserstein distance is binding. So this lambda depends on the reference distribution as well as epsilon, right? And if epsilon gets larger enough, then we're back in the case when we only have the moment constraint. So let's look at the expected shortfall, because then the formulas get a bit nicer and there's better to make an interpretation. So these are the three kind of cases that I looked at. The top one is if we only look at the Wasserstein uncertainty. So we know that in that case, the worst case is the risk measure, so the expected shortfall of the reference distribution, and then a shift, like a plus a constant. And here, the numbers in red are for the choice of alpha equal to 0.99. So we get the expected shortfall of f plus approximately 10 times the square root of your tolerance distance. Then the last one is where we only have the moment constraint. So that will be epsilon for the Wasserstein distance going to infinity. So this we already know this is the mean plus the standard deviation plus also a ratio of that only depends on the alpha. And this again is approximately equal to 10. And the middle case is when epsilon is small enough. So we have the mean constraint, the variant constraint, and the Wasserstein constraint. And here we see this is kind of a more complicated formula that depends on the reference distribution of its mean, its standard deviation, and its expected shortfall. And again, the lambda intrinsically depends on epsilon and the reference distribution. So this is a not so, I mean, the lambda you have to find numerically. Yeah, and of course, if epsilon gets larger, then this approximates this ratio, right? So these are kind of a different example depending on what type of uncertainty set we choose, and what the worst case quanta function looks like in these cases are as follows. On the left hand side, we only have the Wasserstein constraint. So there we knew that's a linear combination of the reference distribution plus the gamma from the, so here this is the expected shortfall. So the blue one is epsilon being equal to 0, so there's a reference distribution which is a standard normal, and then the red kind of dashed line would be epsilon being 0.16. So we see it's the reference distribution and it jumps and accounting for a kind of a larger expected shortfall. And the further, kind of the larger you choose epsilon, the larger that jump is. On the right-hand side, what we have is, if you look at the uncertainty set that includes the Wasserstein distance and the moments. So again, the blue one is the reference distribution, and then the red dashed line would correspond to the same epsilon of 0.16. And there we see it kind of, it has quite a bit of the structure of the reference distribution, but it still has this jump which comes from the risk measure. And if epsilon is large, so in this case, the violet line 0.53, we see that epsilon is too large, and we get kind of the Wasserstein distance is absent, and we get this 2-point distribution that is well known in the literature as the Cantelli bound. So we see this step function there. So this was kind of a little kind of illustration on different types of uncertainty sets. Are there questions?
Yeah, Silvana, there are 2 questions in the chat. Maybe we can just quickly discuss them. Rovanos, would you like to ask them? Or maybe I'll just read them out. So the first question was, please, what do you mean by reference distribution? Does it have to be a particular definition? Mm-hmm. And the second,
okay, yeah.
And the second question was, what is the metric space used in the definition of your uncertainty set?
So yeah, very nice question. So the reference distribution is a distribution that we think is given. So you can think it can come from multiple sources. So you could either have some data where you estimate your empirical distribution. So you could choose the empirical distribution as a reference distribution. You could also say, well, I have some data, fit the parametric distribution, and then you fit your parameter, and that will be your reference distribution. And the interpretation of the reference distribution is, this is a reasonable model for your risk that you want to evaluate, right? And this is, we don't really make constraints on the reference distribution. It doesn't have to be of a particular form. It could be this kind of a discrete random variable. It could be continuous. It could have, you know, finite or infinite support. And for the second question on terms of the uncertainty set, so so far we looked at it very generally. So the uncertainty set doesn't have to have any specific structure. If you just take the supremum, what you want is the supremum is finite of your risk measure. And then in this case, we looked at 3 different types of uncertainty sets where you just have moment constraints. So look at all random variable that have the same mean and variance. And the other one was if you add a Wasserstein constraint on it. So there's just a space of, or a set of either distributions or random variables. I hope that answers the questions.
Yes, thank you.
Okay, great. Yeah, so this was kind of illustration of what are the worst case risk measure look like if you have different uncertainty sets. And as an illustration, I wanted to look at portfolio optimization. And of course, these sets you can generate, these worst case risk measure you can generalize to general distortion risk measure that not necessarily coherent. So this is one example where we look at a variation of a classical setting of robust portfolio optimization. So again, we look at a concave distortion risk measure, and here we have the min-max problem. So we want to find the best strategy. So X is my strategy, or the portfolio weights, in the worst case. So what is exactly I mean with this is we have GR is a distribution of our returns R, and there's uncertainty in the distribution of the returns is such that I only believe and I know the mean and the covariance matrix of my returns. So that would be GR in the uncertainty set of mu and sigma. And then moreover, for every portfolio X, you get an aggregate portfolio return, which I call here GX. And because we know we fix the mean and the covariance matrix of the returns, it has a specific mean and a standard deviation that depends on X itself. So what we assume is that we have a type of allocation scale benchmark distribution F, such that the benchmark changes for every portfolio, but it can be written as a location scale, so mu plus sigma times the reference distribution F. And this, for example, works if you assume that your returns are elliptically distributed. So the idea here is that you have returns on the multivariate level. You only know the mean and covariance structure, and you have uncertainty about its distribution. And then the level of the aggregates, you want to be close to your benchmark in the Wasserstein distance, again in the 2 Wasserstein distance. And here, what is crucial is that the epsilon could depend on your portfolio choice, right? And if you look at this problem, again, you can get some quite nice formulas. So if epsilon is 0, then what you end up is you have to find a portfolio X that minimizes your, minus return plus sigma times the risk measure of F. And then if you increase the epsilon, instead of having the sigma multiplied with the risk measure, you get an increasing function that depends on epsilon. And I didn't put the function h there because it's a bit complicated, but basically if epsilon is 0, you return the risk measure, and if epsilon is large enough, you're larger than constant divided by sigma squared, then you end up in the case where the Wasserstein distance is irrelevant, and you basically only consider the constraints on the mean and covariance matrix. So what does this mean is, well, if you have a larger epsilon, you give more emphasis on the variation on the sigma and less on the expected return, right? And what is also interesting, if you look at the bounds of the epsilon, they always are kind of depending on sigma squared of X. And so one choice one way to choose your tolerance distance is to choose it proportional to the variance of your portfolio, of your aggregate portfolio, which is also sensible because the Wasserstein distance also scales with the standard deviation. And of course, once you specify your reference distribution and your epsilon, you end up with a second order cone program that you can calculate. Right. Another example that I wanted to show with portfolio optimization is a slightly different one, where I don't look at a worst case risk measure, but I use the techniques to kind of answer a question in active portfolio management. So this is a paper with Sebastian Germangel. So here we look at a general distortion risk measure, and we assume that the investor has a benchmark strategy, and however, partially likes the benchmark strategy, but wants to improve upon that strategy, improving in the following sense. So here I wrote down the mathematical problem. So we want to find a pi, which is our strategy. So there's a continuous time setting that we want to find the best risk measure of. So we want to find a better risk measure than the one that the benchmark has. And then of course, if you like the benchmark, but you want to improve upon its risk profile, you have to deviate from the benchmark. So what we choose here is the Wasserstein distance as a potential to deviate from the benchmark. So instead of using the Wasserstein distance as potential alternative distribution characterizing the uncertainty set, we use it here as a potential of how much you can deviate from the benchmark. So we assume that the distribution of the benchmark and the optimal is close in the two Wasserstein distance and particularly bounded by a constant epsilon. Then the last constraint is a budget constraint. So we want that the expected values, the var sigma here is the state price density, is smaller or equal to a pre-specified value. And what you can also add here is a specific state by state dependence. So you want, for example, you want that your portfolio is comonotonic with the benchmark or has a specific dependence structure. So that would be the third constraint or that we add. So how would one solve such an optimization problem? What it turns out, it's kind of uses very similar technique to the robust distortion risk measure. And so I'm not going to go through the details on how you would obtain this, but I wanted to share the worst case, not the worst case, the distribution that attains that infimum subject to this constraint. So that means that so F star will be the distribution of your portfolio, and what we see here, it's a linear combination of the benchmark quantile, so Fx delta inverse is the quantile function of the benchmark at terminal time, the wealth. Then the gamma is again coming from the risk measure, and then here this is a function that derives kind of a transformation of a state price density. So here again, what we have is we have these linear combinations of the benchmark and the risk measure, and the xi here coming from the additional constraint, and the constant lambda 1, lambda 2 are such that the additional constraints are fulfilled. So we have again this nice linear combination. So a couple of pictures that I wanted to share on how that actually looks like. So the black one is the distribution of the benchmark, and the blue is the histogram of the optimal portfolio. And the top left will be the expected shortfall or the T-bar. So again here, because we're in a portfolio setting, my losses are negative, so I want to look at the left tail value at risk. So what we see here in the top left corner is that if we want to improve the expected shortfall, we basically reduce our losses, so we shift the distribution to the right. You could, if you look at the top right corner and plot, what you want to optimize there is you want to increase the upper tail expectation, which means you want to have additional gains, so you're more risk seeking. And what we see is that we shift some of the mass to the right, so we actually get a heavier tail, and then you could do that for additional different choices of risk measures. So as I said, what you also could do is, what we have as a constraint is choosing a specific copula on how you would kind of tie your benchmark wealth to the optimal wealth. So here are two examples of different copulas. So on the right-hand side, we again see the histogram of the benchmark, which is the black one, and the black line is the density of the benchmark, and the blue one is the histogram of the optimal one. So they look fairly similar, but on the left-hand side is a scatter plot of the dependence between the benchmark and the optimal strategy. So the lower part would be a Gumbel copula. So we see it has some kind of joint dependence that resembles the Gumbel copula. On the top one, what we have is a choice of copula that is commutative above a specific threshold and independent below, which kind of, if you have kind of losses, you want to be independent from your benchmark, but if the benchmark does well, you might want to be doing well as well. So these are kind of two different types of application on portfolio optimization, either kind of worst case portfolio or using the technique in a different way. So as the second part of the presentation, I wanted to talk about is the dynamic setting. So far I only looked at a one period time setting, but now what happens if I actually look at a finite time horizon? Because typically if you want to do portfolio optimization, you want to invest over a finite time horizon, right? And there's a couple of questions I'm interested in here in saying is like, how do I quantify uncertainty in a dynamic setting? So can I again create uncertainty sets now in a dynamic framework? And because now in a dynamic setting, I will have to look at a time consistent dynamic risk measure. Can I create uncertainty sets so that my worst case risk measure is still time consistent, right? And is there a way to actually construct one in a nice or a simple way? So these are the questions that I want to look into. So a bit of notation now, looking at a filtered probability space from, let's say, 0 to capital T, and we look at bounded discrete processes. So the notation that I'm going to use is, so 0 to capital T would be the entire stochastic process, and then when I write x t comma s, I just look at the process from time t to time little s. So the way we propose to define dynamic uncertainty sets is as follows. So the idea is that now we have a discrete points in time, and at every point in time, we want to quantify the uncertainty of the stochastic process. So if you think about a static case, what is an uncertainty set? Well, it takes your reference random variable or distribution and gives you alternative set of random variables. So the idea here is very similar. So my uncertainty set at time little t, which quantifies the uncertainty I have at time t, takes my stochastic process and gives me random variable measurable at time little t. Right. So what we assume here is that the uncertainty set is non-empty and it's bounded from above, because we want to look at worst case risk measure. So we want to take the supremum over a random variable in this uncertainty set. Yeah, and this dynamic framework is based together with Marlon and Melina. So a bit of an illustration here. So the way you could potentially view this, so we have a time axis, and at every time point, you have the random variable of the stochastic process, for example, xt minus 1, xt, and xt plus 1. And then the uncertainty set are alternative random variables that could characterize xt. So if you're uncertain about xt, the uncertainty around xt could contain all random variables, for example, for alternative random variables that you would consider. So here, really the uncertainty set, the dynamic uncertainty set, at every point in time, you have such an uncertainty set, right? And for defining a dynamic robust risk measure, I would have to kind of quickly recap some of the notation. So what is a dynamic risk measure? It takes in a stochastic process and gives you a random variable. So here rho t comma capital T takes the process from xt plus 1 up to capital T and gives you the risk summarized at capital T, which now is a random variable measurable at time t. And we call, if capital T is just t plus 1, then we have what is called a one-step risk measure that just measures the risk of the next time step ahead. So if you have now these dynamic risk measures, you can again think about what are properties or desirable properties of dynamic risk measures. And these are very similar to the static case. So you can think about normalization, you can think about convexity, positive homogeneity, and coherence. So these properties are very similar. The only difference is that we have to now be careful because the risks are now random variables, right? But the interpretation is exactly the same as in the static case. Now, what is different is that we have now time consistency, right? So the idea is that we want to be consistent in how we measure risk through time. And one notion that I want to review is what's called order, or sometimes strong time consistency. And the property means if we have two processes there, they're P almost surely the same up to a specific time, and then I know the risk of Z is smaller than the risk of Y, then today the risk of Z should also be smaller than the risk of Y. So it's kind of an ordering of preferences or risk preferences. And so the one-on kind of result here is that if you start with a dynamic risk measure that is monotone, normalized, and translation invariant, then it is strong time consistent if and only if you can write it in this recursive manner where you only use one-step conditional risk measures. And these one-step conditional risk measures are monotone, normalized, and translation invariant. Right. So what is nice about this formula is that first you have this recursion, and also you only have to think about the one-step kind of risk measure, which gives rise to these time-consistent risk measures. So now that we have the dynamic uncertainty sets and dynamic risk measures, we can think of how do we define a dynamic robust risk measure. So what we propose is as follows. So you start with a dynamic uncertainty set, and here it's still very vague, so I haven't made any assumption on the uncertainty set apart from it being non-empty and bounded from above. Then the idea is that you start with a time-consistent dynamic risk measures, which according to the theorem here, you can characterize by one-step risk measures. So here I start with a family of kind of one-step risk measures that are normalized, monotone, and translation invariant. And then I define my dynamic robust risk measures as follows. So I'm going to use R for the robust version of it. So this is a conditional risk measure. So it takes in the stochastic process T+1 to capital T, and I take the worst case of my kind of one-step risk measure where I evaluate all possible random variables in my uncertainty set and take the worst case of it, right? So at time little t, this is a FT measurable random variable and assesses the risk of the stochastic process going forward. And the way I do it, I look at the one-step risk measure, and Y here is now in my uncertainty set, right? So this is a definition of the worst case or robust dynamic risk measure that we have. And then what you could ask is, okay, what are properties on my uncertainty set such that my risk measure has some sort of properties, right? And for example, if you say, well, I started with a coherent dynamic risk measure, if I now add uncertainty, am I still within the class of dynamic risk measure that are coherent? And can I do some if and only if statements? And this will give me some information about how should I suitably construct an uncertainty set, right? So here what we do is we propose some definitions of or properties of uncertainty sets, and the purpose is that the names are the same as the properties of the risk measure. So the idea is if I have a translation invariant uncertainty set, then I should give a translation invariant robust risk measure. So here normalization basically means that the risk of 0 is 0, of a constant is a constant itself. Translation invariant, if you have information that is already known or measurable at an early point in time, that shouldn't increase the uncertainty. Static is if the uncertainty of the risk is just the uncertainty only considering the information at time t, and so on. So we have a couple of different properties that the uncertainty set could satisfy, right? And so, for example, a couple of examples, what you can think of, you could think of how the uncertainty characterized by the Wasserstein distance. So here we probably would want to do like the distance, the Wasserstein distance on the conditional distribution of each step, and then you can see what are the properties that this uncertainty set satisfies, and of course it depends on your tolerance distance, because now your tolerance distance dynamic setting could actually depend on the process, right? And one thing that is kind of interesting is that if you choose the Kullback-Leibler divergence, you get a normalized uncertainty set, where in the Wasserstein distance or general norms, you don't get a normalized uncertainty set. So as I mentioned before, I wanted to have if and only if statements. So for if and only if statements, if you look at the definition of a worst case dynamic risk measure, you take the supremum of an uncertainty set. Right? So the infinitely many uncertainty sets that give rise to the same risk measure. So therefore, to actually get to if and only if statements, what we did is we looked at the largest uncertainty set that gives rise to the same robust risk measure. And that's what we term the consolidated uncertainty set. So basically, it's the union of all the uncertainty sets that whose robust risk measure is the same. Right? And now with that, we actually can create if and only if statements. Let me go here. So R is, for example, monotone if and only if U is monotone, the consolidated uncertainty set, or it's translation invariant if and only if you have translation invariance of the uncertainty set. And of course, if you start with an uncertainty set that has a property, then what we show is that consolidated uncertainty also has that property. So once you start with for example, a translation invariant uncertainty set, then the consolidated uncertainty set is translation invariant, and therefore your risk measure as well. So we do that with many more properties of the risk measure that you would want to have. So in the last couple of minutes that I have, are there questions in the chat, Ludgard, that I should address before I move on to a slightly different topic?
Yeah, thank you. There's one philosophical question. Kami, would you like to ask it? Otherwise, I just read it. So is risk measurable, or price and returns are measurable, and how you allocate a probability to things that we don't have knowledge for measuring of them, such as the risk filtration? And is risk concave or convex in omega FP set?
Oh, that's a very, I think I have to read this. So the way we define our worst case risk measure is we look at the essential supremum over a set of random variables that are already in the right space. So measurability is not the issue here. So how allocate the probability of things that we don't have knowledge of measuring of them, just risk filtration? Yeah, so I mean, the question is how do you construct an uncertainty set, right? I mean, you could create an uncertainty set where that is large enough to incorporate information that you don't know, the unknown unknowns. But this is a very, very tricky question. Yeah. I mean, the idea that we had in this work is to create some ideas of how could you potentially create uncertainty set, or what property they should have. So for example, if you want to have a dynamic coherent risk measure, that is a robust dynamic coherent risk measure, then we should choose uncertainty sets that have these properties. So this is kind of a way to address it, but it's not a constructive way. I hope that answers some direction of the question. Yeah. Okay, so maybe I can move forwards to the second part of the dynamic risk measures, and there is the idea of time consistency. So if you look at this worst case risk measure, what we potentially want to have is a time consistent dynamic risk measure, right? Which is kind of important if you want to do stochastic optimization or control, right? Because then we would get a recursion. So here a quick recap on strong time consistency here in written down for the robust risk measure is when you have these recursion. And what we also have to look at is non-normalized time consistency, because our robust risk measure is not necessarily normalized, which is typically assumed for a dynamic risk measure. So here the only difference is that we have to, we have to subtract the risk of 0 so that we don't count the risk of 0 multiple times. So then what we did is we also defined definitions of what is a time-consistent uncertainty set. So here, let me focus on the strong time consistency. So the uncertainty set of the stochastic process from little t to capital T can be decomposed as the uncertainty of the risk, the process up to time s plus the risk to go, right? So this is kind of a way of defining time consistency of our uncertainty set. And again, this is kind of created such that we get if and only if statement. And again, what we have is R is strong time consistent if and only if the consolidated uncertainty is strong time consistent. And again, if you start with an uncertainty set that is strong time consistent, then your consolidated one is also strong time consistent. So once you start with a strong time consistent uncertainty set, you get a robust risk measure that's strong time consistent, which is all nice. But if you actually look at this definition, it's very difficult to figure out whether your uncertainty set is actually strong time consistent, right? Because it depends on the risk to go, the robust risk to go that already incorporates the uncertainty. So what we wanted to do is there a way of constructing an uncertainty set? And there is. So what we looked at is a static uncertainty set. So these are uncertainty set that only depend on the random variable at that specific point in time. So let's say we choose a static uncertainty set, and then we can define uncertainty set U. So the U var sigma is my static one, recursively backwards in time. So the uncertainty at time t of my process is going to be the static one of the xt plus the future risk to go. And again, we have to take care of what happens at the risk of 0. So if we do that backwards in time, then what we have is that the robust risk measure of my uncertainty U can be written in this recursion, where on the right-hand side we have the robust risk measure of the static with the static uncertainty set. So this way of constructing a time-consistent uncertainty set U gives rise to this recursion. And the risk measure that we obtain is non-normalized time consistent, and if my uncertainty set is normalized, then I end up with a strong time consistent risk measure. And moreover, if I start with a static uncertainty set that is normalized, then I end up with a strong time consistent risk measure. We can actually do something slightly better. We can get an if and only if statement on that sense. So here, this is the if and only if statement. So let's say we start with a normalized dynamic robust risk measure that is strong time consistent. Then we have an if and only if there exists a static uncertainty set such that this equation holds. So this means that any normalized robust risk measure that is strong time consistent can be written as a sequence or a recursion of robust risk measures that arise from static uncertainty sets. Yeah, and so this is kind of a generalization of the work from Patrick Caridito and Brushinsky, where they didn't incorporate the uncertainty and get this kind of a similar if and only if statements for dynamic risk measures. Yeah, so and this was it from my side. So maybe a quick recap. I looked at robust risk measure in a static case, a few applications on how you could use that in portfolio optimization. Also, how could you potentially look at dynamic robust risk measures? There are a lot of future challenges. I haven't answered on or give maybe a little bit of insight of how potentially you could choose some dynamic uncertainty set of what property could be desirable. But of course, there's a big question on applications and also computational challenges on when we will actually want to calculate it or doing optimization. So thank you very much, and I look forward to questions.
Thank you very much. Thank you. Are there any comments or questions? You can raise your virtual hand or type something in Q. Maybe I start. Can you say a bit, like, if you observe, would there, or could you use some sort of learning in your uncertainty set?
You mean in the dynamic setting?
In the dynamic, yeah, exactly, in the dynamic setting.
Yeah, I mean, there's definitely a potential of saying, well, once you actually observed something, you should incorporate that and, you know, reduce your uncertainty going forward, if that's what you mean.
Yeah, exactly.
Yeah, so I mean, for me, it's not clear whether the uncertainty should be increasing or decreasing over time, or I mean, one way to incorporate that a little bit of what you said, like learning, would be if you just look at the, you know, say a Wasserstein distance at every point in time, and then you have the epsilon dependent on your process. For example, it could depend on the conditional variance of the earlier step, right? And there you would change the how uncertain you are depending on the variability one step earlier. But this is just one example that we have.
Yeah. Thank you. Sam, do you want to ask a question?
On this, usually you find you lose a lot of dynamic programming as soon as you do this. So if you make your uncertainty sets dynamic, then generally speaking, do you have any idea whether there are cases that you might be able to find where you get a time consistent object?
I mean the result that we have, let me go here, right, is you basically have these static uncertainty sets, right, where ut only depends on the random variable xt and not, you know, nothing else. So I mean, it depends on how you make it dynamic. There might be ways of doing this, but probably you quickly lose time consistency, right? Yeah, I agree. And then of course calculating that will be even more challenging. Right, yeah.